The last lesson in this chapter is going to be quite different than the previous three. The last lesson in this chapter is on parametric equations, and I'll talk a little bit more about what those are and how they relate to trigonometry that we're doing right now. But let's do a review problem of solving here first. So if you look at this problem, and this is going to be our starter problem, you can see that it is in radians, and it's restricted to one rotation, and it is not multiple angles. However, it is one of those problems where you have two different trig functions, so we have those three options available to us. We could try to factor, and that often involves factoring out the greatest common factor. As you can see in this problem, that would not work at all. Or we could look for an identity to replace one of the two trig functions in terms of the other, or replace both of them in terms of the same third trig function. But again, no identity is available for that. So we're forced to separate these and square both sides and then check when we get done with our answers to make sure we don't have extraneous roots. So what I'll do is I'll first subtract the cosine of x to both sides. So go ahead and do that. That would leave me with the sine of x equals square root of 2 minus the cosine of x. And then, as we saw in a previous lesson, we'll have to square both sides. And this is what requires us to check at the end, because when you square both sides, there's that chance of introducing an extraneous solution. So that would leave me with sine squared x equals, and when you square a binomial, you can use FOIL, or you can use the shortcut for squaring a binomial. The shortcut says to square the binomial, you square the first term. If I square the square root of 2, I get 2. Then I multiply the first term times 2 times the second term, which would give me negative 2 square roots of 2 cosine x. And then I square the last term, which would give me positive cosine squared x. I still have two different trig functions, but as we saw in a previous lesson as well, here we can apply the Pythagorean identity, and I can replace the sine squared with 1 minus cosine squared. And on the other side, I'll just put them in descending order. So cosine squared x first, minus 2 square roots of 2 cosine x, and then plus 2. Now everything's in terms of cosine. So I can move everything to one side, 0 on the other, and I'll choose to move everything to the right side. So I'll add a cosine squared, which will give me 2 cosine squared x, minus the 2 square roots of 2 cosine x. And then when I subtract the 1, I'll just have a plus 1. Now, this one I don't think factors, or at least it doesn't look like it factors, so we're going to use the quadratic formula. And the unknown here is cosine, so I'll have cosine of x equals negative b would give me 2 square roots of 2, because negative of negative becomes positive, and then plus or minus the square root. Now, b squared would be to square negative 2 square roots of 2, and then minus 4 times the a times the c, and that's all divided by 2 times the a. Okay, so far so good. Cosine of x equals, I have 2 square roots of 2. When I square the negative 2 square roots of 2, I would have 8. So I have 8 minus 8, which gives me a 0. So I have minus the square root of 0. Now the square root of 0 we know is just 0. And on the bottom we still have 2 times 4. Oh, sorry. The bottom we have just 4, because 2 times 2 is 4. So the square root of 0 being 0, I could just reduce this and have the cosine of x equals square root of 2 over 2. Well, that turned out much better than I expected it to, because that one will have a reference angle. So the reference angle would be an angle where the cosine is positive, square root of 2 over 2, and we're in radians, so that's 45 degrees in degrees, pi over 4 in radians. Positive cosine occurs in quadrant 1 and quadrant 4. Now, in quadrant 1, it would be just our reference angle, pi over 4. In quadrant 4, it would be 2 full pi's, which would be 8 pi over 4 minus 1 pi over 4. So we would have 7 pi over 4. Okay, but we have to remember that we're going to have to check. Now, in quadrant 1, both of them are positive. So if I was checking, I would have cosine of pi over 4 plus sine of pi over 4. And we're checking to see if that's going to be equal to square root of 2. Well, that's square root of 2 over 2 plus square root of 2 over 2. And that's 2 square roots of 2 over 2. And that does check. So pi over 4 does work. The quadrant 4 angle is not going to work because in quadrant 4, although cosine's positive, sine will be negative. So this one was an extraneous root. It was introduced when we squared both sides. So I put that one as a class starter just to remind you that if you have to square both sides, you simply must check to make sure that you have the roots are all valid solutions to the original problem. So on with this lesson. And this lesson is actually going to have quite a bit to do with conic sections. Conic sections, if you remember from your Algebra 2, were circles and ellipses and hyperbolas. This first one is a circle. This is the standard form for a circle from Algebra 2. The center is at HK. So the center for the one I have here is at 1, -2. The radius, well, this number over here is r squared. So the radius would be 2. So if I was going to graph this, I would go over to 1, -2. And then I would move out 2 in all directions, 2 to the right, 2 up, 2 to the left, 2 down, and I would just draw my circle. Now, circles you did back in geometry, you did them again in Algebra 2, and you may even have done a little bit of them in Algebra 1. Let's talk about the other conic sections. So this was the standard form for an ellipse. And in an ellipse, we still have a center. So the center is still at HK. So in this case, -2, +1. But once we go to that point, so -2, +1 right here, then we take the square root of what's beneath the x. So that means we're going to move out 3 in the x direction. So 3 to the right, 3 to the left. And then we take the square root of what's beneath the y. So 5, that's how much we move in the y direction. 1, 2, 3, 4, 5 up. 1, 2, 3, 4, 5 down. And then we draw our ellipse. An ellipse looks sort of like an elongated circle. Your Algebra 2 teachers may have told you that. It has what's called a major axis and a minor axis. Just to remind you, the major axis simply means the longer direction. So here the major axis would be the vertical one and the minor axis would be the horizontal one. And that's how we graphed ellipses back in Algebra 2. The third and final conic section that you studied back in Algebra 2 was called a hyperbola. And a hyperbola had nearly the same form as an ellipse, except it had a subtraction in the middle. And that's how we knew it was a hyperbola. We still had a center. Now keep in mind for the center that the x part has to go first. So 1, -3. So if I go over 1 and down 1, 2, 3. And then a hyperbola also had a major and minor axis. So if we look beneath the x, the square root of 16 is 4. So I'll move out 4 in the x. 1, 2, 3, 4. 1, 2, 3, 4. And then we take the square root of what's beneath the y. So I move 2 in the y direction. And this is where it became quite a bit different. So we actually form a box often called a reference rectangle. So I will go down vertically on these sides, and then I'll go across horizontally and then we draw the extended diagonals of this box. So the extended diagonals would go from corner to corner. So one extended diagonal would go like that, and the other extended diagonal would go like this. Notice they go through the center, and they go from corner to corner. And now we look at the variable that came first. So the variable that came first, being the y, that tells us that this particular hyperbola is longer in the y direction, or it actually opens in the y direction, rather. So we start at our point on the reference rectangle, and we get closer and closer to these asymptotes. Oh, let me make that last one a little bit better, because we have to get closer and closer. And then we start at this point on the reference rectangle and get closer and closer, and closer and closer. And that's just a review of your Algebra 2 graphing the three conic sections that we'll be seeing. So let's see how it applies here in trigonometry. So parametric equations. So many times in mathematics, there'll be a set of points, x, y, that are described in terms of a third variable. Oftentimes, it'll be t, standing for time. So they may say that the x is defined to be a function of one trig function, and the y is defined to be a function of another trig function. And they'll give you the description of this particular shape or graph, but they'll give it to you as a pair of equations where both x and y are defined in terms of that third variable, in this case t. So in trigonometry, what we'll be trying to do is eliminate the parameter. Eliminate the parameter means to take that pair of equations where x and y are both defined in terms of a different variable and rewrite it as a single equation back in the form that we're used to, where it's one single equation just in terms of x and y, and we've eliminated that third variable, which is called the parameter. So again, we're going to be focusing on eliminating the parameter. So the process is going to be to start out with these parametric equations, and then you'll take each equation and you'll try to isolate the trig function. So in the top one, for instance, I can isolate that trig function by just dividing by 3. So I'll have x over 3 equals the cosine of t. And in the bottom equation, I can divide by 2. So I'll have y over 2 equals the sine of t. And then because we're dealing with conic sections, we're going to use one of the three, Pythagorean identities. And we'll actually be using just 2 of them. So the one that we're going to use that's a Pythagorean identity is the one that involves sine and cosine, because those are our trig functions in this problem. So that identity looks like this: sine squared of t plus cosine squared of t is equal to 1. And now we'll replace the sine of t with y over 2. And that's being squared. And we'll replace the cosine of t with x over 3. And that's being squared. And now we will simplify, because this is not quite in standard form. We've eliminated the t in there, but we'd like to put this in the standard form. So when I square that first one, I have a y squared on top, and and I have a 4 on the bottom. When I square the second one, I have an x squared on top and a 9 on the bottom. When I look at this, at first it may look like it could be either a circle or an ellipse because we have a positive between the x squared and y squared. But because there are different numbers that are beneath the x and y, that makes this an ellipse. And one of the things you have to be able to do is you have to be able to classify this. So we would classify it as an ellipse. Now the center of this ellipse, that's supposed to be at h and k. H is what is added or subtracted from the x before it was squared. Well, there's nothing up there with the x, so that's 0. K is what's added or subtracted from the y before it was squared. There's nothing up there either. So 0, 0 is our center. To figure out how far we move in the x direction, we take the square root of what's beneath the x. In this case, that would be 3. To figure out what's beneath, or how far we go in the y, we have to take the square root of what's beneath the y. So we would go down 2 and up 2. And now we're ready to sketch our ellipse. So our ellipse would be longer in the x direction and look something like this. The three things that you have to be able to do is you have to be able to eliminate the parameter. That would give you this, the standard form for your equation. You have to be able to identify the conic. It will be ellipse, circle, or hyperbola. And you have to be able to sketch the graph. Let's do a second one of these. Okay, just to remind you of the process is to first isolate the trig functions. So to isolate the sign up here, I'll subtract 3. I get x minus 3 equals sine of t. And for the cosine, I would add 2. So I would have y plus 2 equals the cosine of t. Since we still have sine and cosine, we'll still use the same Pythagorean identity. Sine squared plus cosine squared equals 1. That was one of the Pythagorean identities you memorized. In place of the sine, I will put the x minus 3, and that quantity is squared. In place of the cosine, I will put y plus 2 squared equals 1. Now, this actually is completed. This is eliminated the parameter. This is a standard form. Because there are not different numbers beneath the x and the y, both of them would have a 1 down there if we thought of it that way, this would be a circle. So that's called identifying or classifying it. When we go to graph it, we would need to know the center. So the center here would be at positive 3, negative 2. Notice it's the opposite of what's in the parentheses with the x and the opposite of what's with the y. So if I go to 3, negative 2, I would be right here. And the radius is the square root of what's over there. Now the square root of 1 is still 1, so the radius is 1. And then we go ahead and sketch our circle. Okay, let's try yet another one. First step, isolate the trig function. Now, to isolate the trig function for the secant, I will have to do two things. I'll have to subtract the 3 and divide by 2. So that would give me x minus 3 divided by 2 equals the secant of t. To isolate the tangent in the bottom one, I would have to do two things as well. I would have to subtract 2 and then divide by 4. So I would have y minus 2 divided by 4 equals the tangent of t. Now, as you can see, we're not going to be able to use the same Pythagorean identity here. And that's because we don't have sine and cosine. We're actually going to use the Pythagorean identity that looks like this when we first saw it. It is 1 plus tangent squared of theta equals secant squared of theta. But we're going to move the tangent squared over. And that's going to give us secant squared, and I'll put a t in there, minus tangent squared, t equals 1. And now we'll go ahead and we'll replace the secant with x minus 3 over 2, and that whole quantity is squared. We'll replace the tangent with y minus 2 over 4, and that whole quantity is squared. And again, this is not a standard form for any of our conics, so we have to go a little further. We don't have to square the binomials. We can leave that as x minus 3 squared. I will have to square the bottom number. And y minus 2, quantity squared, over 16 equals 1. This would be our answer for eliminating the parameter. This is the standard form of our conic section without the t involved. And as you can see by the subtraction in the middle, this one is a hyperbola. This is the one where we have to make the reference rectangle, draw in those extended diagonals as our asymptotes, and then decide if it's vertical or horizontal. So the center here is going to be at positive 3, positive 2. Positive 3, positive 2. In the x direction, I have to take the square root of 4, so I go out 2 in the x direction. In the y direction, I take the square root of 16, so that's 4. And now comes the reference rectangle. And to remind you, the reference rectangle, we go vertical through the two endpoints on the left and right. We go horizontal through the points on top and bottom. And then we sketch the extended diagonals. So the extended diagonals have to go through the center, and they have to go through the corners. So there's one extended diagonal. There's the other extended diagonal. And now we have to decide, is it going to be on top and bottom, calling it a vertical hyperbola, or on the left and right? And that is completely determined by which variable came first. Since the x is first, the x is positive, we start on the x edge of the box, and we get closer and closer to those asymptotes. And then we do it again on the left side. They do not curl back in. They get closer and closer to the asymptotes, but they don't come back in. So this one was horizontal. If you think of the one we did as a practice at the very beginning, right after the class starter, it was a vertical one because the y was positive. The y came first. So that is the last section. That's parametric equations. Once again, you have to be able to do two things, or three things. You have to be able to eliminate the parameter. And that means to rewrite it as a single equation in terms of just x and y in regular standard form from Algebra 2. You have to be able to classify it. That means you have to be able to tell us if it's a hyperbola, ellipse, or circle. And then you have to be able to sketch it. So you need to practice all of those. And if you look at the homework, you'll see that I just drew coordinate axes in the homework rather than provide graph paper. Okay, well, good luck.